description. So the patients can be divided either in 3 or 2 groups. If we divide them,
microphone, please.
oh. So we can divide them according to their health status. So there are some patients which don't suffer from multiple sclerosis. There are some that suffer from familial form of multiple sclerosis, and there are some that suffer from sporadic multiple sclerosis. But data also come from 2 different laboratories, mainly for the first one, and we will see that these 2 different environments somehow influence the results. Each patient is described by approximately 200,000 features, which are all numeric and take values from 0 to either 0, 1, or 2. And they are describing the presence of genetic variants. Each of them is describing the presence of genetic variants at a single locus as compared to the reference genome. So if the value is 0, then the reference sequence is found on both strands of DNA, and if the value is either 1 or 2, the genetic variant is present on 1 or both strands of DNA. And the target variable is the state of the patient. We now come to the feature ranking algorithms. So I will give just the motivation for both. Gini3 is the first one, and it is based. It is ensemble-based feature ranking algorithm that is computed from a forest of decision trees. Here is an example of a decision tree, and in the Gini3, a feature is considered important if the group of examples that come to one node is far more heterogeneous than 2 groups that come from this node. And in pictures it's like that. So we have here quite heterogeneous group, and if the feature is relevant, these 2 subgroups are then much more homogeneous. Here is a technical definition, but I will skip this. So the next one and the last one is relief F. This is an iterative algorithm which where on each iteration which randomly choose one patient and compute its nearest neighbor. And here the feature is considered relevant in the next 2 cases. So if the target values are different, so for example one patient suffers from multiple sclerosis and the other doesn't, then also these feature values should not be similar, because then we can see this difference in feature values as one of the reasons for the change of class variable. And also if the class values are the same, then also the feature values should be the same. Again, here is technical definition of the algorithm, but we will also skip that. And we came to evaluation methodology. So for each of the ranking algorithms, we first compute feature ranking from the training set, and then for different numbers of features, we build predictive model which are support vector machines on the training part of data, and this predictive model considers only the top k ranked features, and then we evaluate the predictive model on a test set. And when we plot the results, we obtain one curve for each feature ranking. So here is the number of features, and on the y-axis there is the accuracy of the corresponding model. So we can see that at the beginning, we will just zoom in those 2 curves. So we are only interested at the beginning of the ranking. So here is the plot for the first 4,000 features. So at the beginning, we can see that all relevant features are added to those feature sets because the accuracy increases fast. And we can also see that Gini3 returns better rankings because it achieves its highest accuracy its highest accuracy is achieved before, is higher than relief's highest accuracy, and also this accuracy is achieved with quite small number of features as compared to the relief's one. So here are the comments that I have already mentioned, and so from all this we can conclude that Gini3 produces better rankings. And also, I can also mention that more features doesn't mean necessarily higher accuracy, because if there is some noise in the data, the accuracy will drop eventually. We have also checked how, as mentioned before, how different laboratories influence the rankings. So we compared the similarity, we computed the similarity between the ranking that based on the data that comes only from the first laboratory and the data that comes from the both laboratories. We compute Jacquard's similarity index that compares similarity of the sets of the top features, and again we can plot the curves where on the x-axis there is number of features and similarity index on the y-axis, and we can see that Gini3 rankings are less stable than relief F's at the beginning, but they are still more stable than two random rankings are, which is denoted by this dotted line. So conclusions are as mentioned, and to conclude, we have actually sent those results of Gini3 rankings to our collaborators, and they analyzed a small set of top ranked features, and they found matches to genes that have already been reported in the literature to be associated with multiple sclerosis. And in our future work, we'll run our algorithms on the new data, which was prepared using new pipeline that takes into account these two different environmental conditions. And also we'll try to tackle this problem from the hierarchical classification point of view, since the class values can be organized into a hierarchy. And with that, I conclude.
Yeah. Questions, please?
Interesting question. Can you comment a bit, can these findings be generalized when you are comparing the two different algorithms? For example, how much is dependent on the data set and how these algorithms the machine learning algorithm?
Generalized to what?
What if I use random forest, for example, instead of SVM?
Yeah, well, I think, of course, there has been some research done in that direction, and it turns out that for these general data sets, for example, from UCI repository, SVMs turned to be appropriate, and there were, I think, random forests were also appropriate. Well, here the reason is that that literature suggested SVMs, but in general, I think any learner that is strong enough can be used.
I meant whether the relief has to run better if we use another.
Aha, well, we don't actually know, and we should try, I think. Maybe k nearest neighbors, if something there, maybe something can be said about k nearest neighbors and relief F, because the main part of relief F is finding those nearest neighbors. So maybe k nearest neighbors would prefer relief F, but for the other algorithms, I don't know.
I would like to comment briefly. In
Yeah.
conclusions did not change. It was not exactly these data sets, it was other data sets, but in particular the results of the comparison did not change.
Okay.
Any other here?
My impression is that these two feature ranking algorithms take the dependence between features into account to some degree, but I'm not really sure. Can you comment on this?
Your impression is right. If in the case of Relief F, we somehow capture those dependencies with computing nearest neighbors. So if we believe that small perturbations are the right way to capture the differences, this is the explanation. And in the case of the Gini tree, each next node somehow depends on the previously defined tests. So random forest or decision trees in general can also somehow capture those dependencies. And since the Gini tree is computed directly from the trees in the forest, the dependencies should be taken into account.
Do you have an explanation of why is Gini tree better?
Yeah, so I think so, because here is the evaluation procedure as we take it in general. But here is the situation is somehow special, because those people from KIMC wanted just one feature ranking. So what we did is we actually take the whole data set, because we try to believe that since the random forest is built by using bootstrap replicates of the data, and for that reason no tree sees all the data, we took this approach and then aggregate the feature rankings. Well, okay, so when the ranking was computed, this is actually a ranking which is aggregated over all trees. And then we report this ranking. But since we used 1,000 trees, maybe this... so actually the ranking have seen all the target variables. Implicitly, since this was taken as the average over all the trees, but still. So I think this is also the reason for that 100% accuracy. And yeah, when you are 100%, you are better than everyone else. So.
You presented here only one domain, only two algorithms compared in terms of attribute selection. And for example, there are about 30 maybe well-known algorithms for attribute selection.
Yeah.
So the idea seems very interesting for the algorithm, but maybe you should really do a thorough testing. What's your comment?
Yeah, we probably should, but as said, this is the data that our collaborators were not so satisfied with. So we more or less run these preliminary tests and see what comes out. But sure, we can try more than 2 feature ranking algorithms. Yeah.
Okay, thank you very much.